In this lecture, we'll start the discussion of the fields inside metallic waveguides or resonant cavities. The ultimate goal would be to understand how we find the configurations of the normal modes and the corresponding decay parameters. The first step, which we'll do in this video, is to obtain some general understanding of the configuration of the fields near the surface of a conductor. First, let's recall what we know about the fields inside the conductor. We can write the wave equation that goes as del squared plus mu epsilon omega squared, and here we can have either the E or the B field, and that's a 0. So remember, everything will be written for a monochromatic field amplitude. So here we have omega corresponding to that field. And if we look for a solution in terms of a plane wave, we find that the wave vector, if it's given by omega times the square root of mu epsilon. We also know that the dielectric permittivity can be written as 1 plus I sigma of omega divided by omega, assuming that all the current in the material has been folded into the definition of the conductivity sigma. When we talk about waveguides, we have in mind some metallic tubes or cavities with a characteristic size of a few centimeters. So let's say we take a wavelength corresponding to that of the order of 3 centimeters. So the corresponding frequency, which is C divided by lambda, will then be of the order of 10 to the 10 hertz or 10 gigahertz. So this is roughly the range of frequencies we're interested in the waveguide theory. Can be 10 times less or 10 times larger, that doesn't matter. And we note that this frequency is such that if you take a good metal, then in a good metal, for the frequency corresponding to this, omega tau is still much less than 1. Because of this, the conductivity in the formula here is essentially its static limit. So the omega dependence doesn't matter. Sigma of omega is approximately real. So it's approximately equal to the static conductivity. And the term with sigma divided by omega is much larger than 1. So the first term in this expression is small. Epsilon is close to purely imaginary. That epsilon goes under the square root here. And then you get the expression for k that has equal real and imaginary parts. And we can write it as 1 plus I over delta, where delta is the so-called skin depth. And the skin depth can be found by substituting the expression for epsilon under the square root. And this will give us delta equals square root of 2 divided by mu omega sigma. This tells us that the electromagnetic wave decays into the metal at the length scale of the order of delta. Now, at microwave frequencies, so at the frequency of 10 gigahertz, this delta in good metals, such as copper, aluminum, or anything of that sort, will be of the order of a micron, or a little less than a micron. This micron is much less than the wavelength in vacuum, which is here of the order of 3 centimeters, as we assumed. To make it clear that there are two different wave vectors involved, let's apply a subscript c to k in the conductor, and then reserve k for the wave vector in vacuum. So that's just 2 pi over lambda. So by comparing lambda and delta, we see that in this problem, we have a small parameter, k delta, which is much less than 1. The existence of the small parameter will be the key to our subsequent considerations. One more thing we can notice at this point with respect to the two terms in epsilon. So here in this expression, we have a term that is just one that comes from the electric field, and then the term from the conduction current. In fact, I wrote this term in Gaussian units. Let me correct that and rewrite in SI. So instead of 1, we would then have epsilon naught here. So let's compare this, this first term, epsilon naught, with the second one. So we can write the ratio epsilon naught divided by sigma of omega. So I have epsilon naught omega divided by sigma. And then use the definition for delta to substitute 1 over sigma as delta squared times mu omega. So I have epsilon naught omega mu omega delta squared. So I have 2 powers of omega, and then I have epsilon naught mu. Now, assuming that mu in the conductor is of the same order as mu in vacuum, so the metal is non-magnetic, then epsilon naught mu is just 1 over c squared. So I have omega squared over c squared times delta squared. Omega over c is k, so this is just k delta squared. And we know that k delta is a small number, so k delta squared is still an even smaller number. To keep things compact, we can define a new quantity that we can call sigma star of omega, such that epsilon of omega is defined simply like this. So this sigma star would be equal to sigma of omega minus I omega epsilon naught. Now, if we're only interested in the leading terms in k delta, then the difference between sigma star and sigma will be negligible. In any case, sigma star is just a number for the given frequency that may have a small imaginary part, but in combination with the fact that omega tau is much smaller than 1, we always have that sigma star in our regime is just approximately equal to the static conductivity sigma sub 0. Let us now write Maxwell's equations in the conductor. The equation for the curl of H contains epsilon E dot. So we have folded in the current density J into the definition of epsilon. So there is no term with J. And this is, in fact, simply sigma star times E. The curl of the electric field is given by negative B dot, which becomes I omega mu H. So again, remember that everything here is written in terms of complex amplitudes for the monochromatic wave case. So for example, E here is assumed to be written as the real part E of R e to the minus I omega t, and all the equations that we write here contain this complex amplitude E of R and H of R here. The other two equations are del H equals 0 and del E equals 0. We're dealing with fields inside the conductor where epsilon and mu are constant, so the equations can be written for B and D and just as well for H and E. Our first question is to figure out the configuration of the fields in the limit where the small parameter k delta goes to 0. So that's the 0th order term in the solution of the Maxwell's equations. So first, let's look at the first of the Maxwell's equations and see what we can find about the electric field. So in fact, taking the first equation, we can write that E, which is equal to 1 over sigma star curl of H. There are two kinds of derivatives involved here. There is a derivative in the direction perpendicular to the surface, and derivatives in the directions parallel to the surface. The derivative perpendicular to the surface, let's call it delta sub n, will give us something of order 1 over delta. Why is that? Well, we know that because the k vector contains an imaginary part of order delta, so the fields decay on the length scale delta. So d by dz, where z is perpendicular to the surface, will give us something divided by delta. Now, derivatives parallel to the surface, let's call it delta tangential, will give us something of order k. Right? The variation of the fields parallel to the surface happens on the length scale of the wavelength. So you'll have 1 over lambda or k in the numerator. So it's clear that the largest terms from taking derivatives will come from the normal derivatives. 1 over delta is large compared to k because k delta is a small parameter. So taking this larger factor, 1 over delta, we can estimate the electric field as being of order 1 over sigma times delta H. Now, 1 over sigma delta, as can be found from the definition of delta, is of order mu c k delta. Now, if we look at the connection between the electric and magnetic fields, if we took away the factor k delta, then E of the order of mu c h would be of the order you expect the field to have in vacuum, given the magnetic field. However, here we have an extra factor k delta, that is a small parameter. So we find that the electric field in the conductor is small by the parameter k delta. So the leading field is magnetic. Speaking about the magnetic field, let's write the divergence equation now in two parts. So del H can be written as del transverse, H transverse, plus dHz by dz, where z is the direction perpendicular to the surface. Now, we know that d by dz is of order 1 over delta, and del t is of order k, as we just discussed. So we find that hz now is of order k delta times h transverse. So the normal component of the magnetic field is also small by parameter k delta with respect to the transverse field. So we find that the leading field near the surface of the conductor is the transverse component of the magnetic field, and then the electric field and the normal component of the magnetic field are small by the parameter k delta. So in the limit k delta goes to 0, the field will be dominated by the transverse h sub t. Thus we see that in the limit k delta goes to 0, we have the 0th order electric field vanishing, and the magnetic field is dominated by H transverse, which, as always, satisfies the wave equation. Where the dominant derivative is normal to the surface, so I can just keep the z component of the Laplacian. That's the d2 by dz squared. The solution of this equation gives us ht naught, that's the 0th component of the parameter k delta, goes as some value at the surface, let's call the argument 0, set z to 0, distance from the surface, e to the I kz, where k is the wave vector in the conductor, and that's 1 over delta 1 plus I. Of course, this solution is only true locally, so this value of the field that we have assumed is the local value of the magnetic field at the given point on the surface of the conductor. The fields at different points are different, but this expression here tells us how the field decays into the bulk of the metal at the given point in the reference frame where the axis z is chosen normal to the surface. These conclusions tell us what the boundary conditions should be on the vacuum side of the metallic surface in the limit of a perfect metal where the parameter k delta is small. Because the electric field inside the conductor should be 0 in this limit, then outside of the metal, right next to the surface, the E tangential on the outside should vanish. The tangential component of the electric field is continuous at the surface, so it's 0 inside, should be 0 outside. The normal component, in fact, can be large outside because epsilon is discontinuous. Now, in addition, because the normal component of the B field is continuous, right? So the divergence equation for B tells us that B normal out should be equal to B normal in. We assume that there's nothing special about the dielectric permittivity's mu. So usually we use a non-magnetic metal, in which case mu is very similar in and out of the metal. They're both close to mu naught. So the continuity of B sub n essentially implies the continuity of H sub n, or at most they differ by a small factor given by the ratio of mu's. And on the other hand, we know that in this limit of small k delta, the magnetic field is purely transverse inside the metal. So there is no normal component inside the metal, and therefore we find that H n out is also 0 in this limit. So if all we are interested in is the approximate configuration of the fields in vacuum next to the surface of a conductor, approximate in the sense that we assume k delta is strictly 0, then we can solve the field equations in the vacuum subject to these boundary conditions. Tangential component of the electric field vanishes at the surface of the conductor, and same thing goes for the normal components of the magnetic field. If that's all we need, then we don't need to go any further with a discussion of the fields in the conductor. Now, in order to find the decay parameter for any modes in the waveguide or resonant cavity, we need to know the electric field to first order in k delta. So why is that? Well, simply because if the electric field is 0, then the power loss, which is the energy flow through the surface of the conductor, which is given by the Poynting vector, right? So we have the Poynting vector, that is E cross H star. Well, there's also 1/2 and real part is assumed, but if the electric field is 0, then the Poynting vector is 0, and no power, no energy flow crosses the surface of the metal. So in other words, in the 0th approximation, S0 is just 0. There is no power loss. In order to find the power loss, we need to go to first order in k delta. So to find the power loss, we need to know E to first order. We don't need H to first order because E to 0th order is 0. So if we find E to first order, then we'll find the first order for S order in parameter k delta, which goes as 1/2 real part E1 cross H0 start. Now this S1 will give the Poynting vector, and the actual power loss, we can call it dP loss by dA, will be given by the projection of the Poynting vector onto the surface normal. So if the external normal to the metal is N, then you just dot it with S. And the leading order in the power loss will be given by S1 order of the Poynting vector. To find the first order in the electric field, we can come back to one of the Maxwell's equations. So remember, we had an equation that curl of H is equal to sigma star E, where sigma star is essentially the same as sigma. So then from here, we find E equals 1 / sigma star curl of H. Now again, remember, if we take the derivative, we get at most the factor 1 / delta. So 1 / sigma delta is of order, as we found before, of order mu c k delta. So that's where the first order comes from. Now, we can expand E and H in this equation in powers of k delta and match the powers, because del over sigma star gives it extra power of k delta. Then the 0th order in H will give us the first order in E. With this in mind, we can easily write for the first order in the electric field, we can write 1 / sigma star del H0, where H0 comes from the solution in the absence of the correction, namely to 0 order in k delta. Now, if we want to get this leading order in k delta, as we just discussed, we need to get the 1 / delta from the del operator, which means that we're taking the normal derivative of the magnetic field. So approximately this del operator can be replaced by negative n d by dz, where n is the surface normal. So then this E first order in k delta goes as minus 1 / sigma star n cross dH naught by dz. Note that this first order in E turns out to be purely tangential to the surface because of this cross with the surface normal N. So now, putting everything together, we know how to find the leading order in the Poynting vector. That gives us the power loss through the surface. We know the leading first order in the electric field that goes into the expression for the Poynting vector. We know that H naught is tangential to the surface. The electric field is also tangential because of the cross with N in the expression for first order E. And we also know that the power loss per unit area is given by the projection of the Poynting vector onto the surface normal. So if we put this all together, we will find for the power loss the expression that goes 1/2 sigma delta, and then here I have the absolute value of H naught squared. The factor 1 / delta appears from d by dz. Remember, we have this expression for the magnetic field as a function of z, so d by dz gives us I kc, and I kc is 1 over delta 1 plus I. And then we need to take the real part in the expression for the Poynting vector. So that gives us 1 over delta, and of course the power flows out of the vacuum and into the metal. Thus, collecting everything together, our general strategy for solving waveguide and resonant cavity problems will be the following. So in the first step, we're going to solve the Maxwell's equations in vacuum in the area enclosed by the waveguide, subject to the boundary conditions that we found before, that the normal component of the magnetic field vanishes at the surface of the waveguide or resonant cavity, whatever that is, and that the tangential component of the electric field also vanishes at the surface. Now, in the second step, if we want to find how those field configurations decay due to the power loss through the walls of the metal, that is essentially ohmic loss in the thin region next to the surface of the metal where you have currents. So that's the skin depth. So to find the power loss, we just use the formula dP loss by dA, where we substitute the solution that we found in the first step. And we will want to integrate this power loss over the surface of the conductor. This concludes this video lecture.